Hello everyone. In this video, we are going to cover D1 gravitational HL part of this video. We have already covered the SL part of this chapter, and now we are going to cover the HL part of this. Now, in this is a copy of a syllabus guide where we have covered all this content that was given in SL part. Okay. Now we are going to focus more on the HL part. Now, what we are expected to know from the HL part of this chapter is gravitational potential energy and how the work is done to assemble the masses from infinite separation. Then we have gravitation potential energy definition. We need to have gravitation potential energy definition, like work done per unit mass and bringing a mass from infinity to that point. Similarly, we should know the gravitation field strength, how it can be calculated from the gravitation potential. Then we need to know work done to move a mass in a gravitational field. We have equipotential surfaces and some energy relationships like finding escape velocity and orbital velocity, and some qualitative effect of how small viscous drag force due to atmosphere on the height and the speed of orbiting body. Okay, so we're going to start with the first important part, that is definition of gravitation potential and potential energy. So we are going to cover the first part of that. So gravitational potential. Now, what is gravitation potential? It is understood as work done per unit mass. Work done per unit mass to move a mass from infinity to a finite position in the presence of gravitational field. Okay, and it is expressed using a formula, that is Vg is equal to negative Gm over R. Okay, now what does exactly this formula means? What does each term represents? We need to understand that as well. So Vg represents gravitational potential energy. Gravitation potential, and this M represents a source mass, source of a field. R is the distance where the potential is calculated, and this is the distance from the center of source to that point. Okay, so it is gravitation potential and its unit is joule per kg. Okay, so this is the gravitation potential part. Then, along with gravitation potential, we immediately introduce gravitational potential energy because they both have almost similar meaning. So, what is gravitational potential energy? So, according to the name suggests, it is a work done or some relationship with the energy. So, it is a work done to move a mass from infinity to finite position. So, this formula will be given as Dp is equal to negative Gmm over R. Okay, so Gmm are the two masses. The one mass is the source mass, and the small m is what the mass or a test mass we can say, the mass we are trying to move. R is the distance between the masses, and the more important part is why there is a negative sign. We have seen that negative sign in both gravitational potential and potential energy. So we need to make a note that for attractive forces, for attractive forces, the potential energy is always negative. Okay, so this is the case. In case of electric forces also, if the forces between a positive and negative charge is attractive, in that case the potential energy is also negative. Okay, the unit of this potential energy will be joules. It is just an energy. Okay, now unlike electric gravitational field and force, potential energies are scalar quantities. Okay, so with an example we will understand how we can calculate a potential energy between 2 points. So let's say there is a mass m1 and then there is a mass m2. Okay, now they are separated from a point which is p, and the distances is r1 and r2 between them. Now the question is, what is the potential gravitation potential at p? Okay, so in this case we need to remember that gravitation potential is a scalar quantity. If this was a vector, I would have been drawing a vector, individual vectors, and then take a result out of them. But this is not required here. The net gravitational potential energy is the individual sum of individual potential energies. So this is the case. Okay, and this would be the other one. Okay, so it is just a sum of individual potential energies that we need to add, and we will get our answer. So we don't have to do anything related to vector. It is very much straightforward calculation when we want to find a net gravitational field. Okay. Apart from this, the gravitational fields or the potential and potential energy has like we can draw graphs based on potential energy versus distance graph for different scenarios. So gravitation potential versus R graphs. So we will look at different scenarios of this. The first scenario I'm going to talk about is the point mass. Okay. Now, since potential energy is negative, the gravitation potential is also drawn on a negative axis. If this is R versus Vg graph, since Vg is equal to negative Gm over R, we can, this is for point masses, for a point mass. So we can draw this. It will probably look like something like this. Okay. So since a negative 1 by R curve, okay, it is negative 1 by R curve, so it looks like this. Okay. Then the another graph we can probably explore is the like a spherical mass. And radius of the sphere is R. So in this scenario, if you look at the graph, the graph will look like the, yes, sorry. So the graph will look like something that starts from R, like from the radius. We're going to explore this graph from the radius. Okay, we are not worried about what will be the graph inside. It won't be asked, so we don't have to worry about it. But we need to know what is the starting point of this. The starting point of this will be negative Gm over R, the capital R, and then it keeps on decreases with respect to 1 by R. So this is for a spherical mass. Then the another case that we will see in this is that what if there were two masses simultaneously, okay, two spherical bodies. In this scenario, we want to understand that there is a planet M, let's say X, it has some radius R and mass M. It is roughly around a certain distance, let's say from a planet Y, which has a radius R dash. Okay, and the distance between them is what we given as D. Okay, now if I try to plot and depict same things on potential versus R graph, it will look like Vg over minus R, and here it will look like, for example, it will start at some R, the radius of this planet, and it will have a more minus Gm over R, so that is a higher mass. Let's say the mass here is also M dash. So it will start from here. Now for the other mass, it also has a radius, some R dash has a radius. So we will take it from the surface and it will have a smaller negative Gm dash R dash as a potential, which you can draw here. Now between those 2 points, what happens is like the potential energy first decreases and then it increases. Okay, so this is how we are supposed to draw it. Now, the one important point in this particular graph that I would like to make is the point where we can reflect something like this. Okay, here the gradient of the graph is 0. Okay, now what does this represent? This point represents a position where gravitational fields from both the planet cancels out each other. So basically there is no net field. Okay, so here we can figure out one important relationship is that the relationship is G is equal to negative, or even if it is negative, just if we take a gradient of the potential versus R graph, we will get the gravitational field strength. This is very important relationship. So gravitation field strength, and specifically only the magnitude of this, because it is a vector quantity, so we won't get the direction. Magnitude of gravitation field strength is equal to the gradient of Vg versus R graph. Okay, so this is the first scenario that we will talk about, and once we get this, there is a simplified version of this as well. Okay, but before that, we would like to explore what is equipotential surfaces. So in equipotential surfaces, it is a a collection of points around the source of the field where the potential energy or potential is same. Okay, so it is, for example, if I have a planet like this of mass m, the potential at this point depends on the mass and the distance from this. That distance is r. Now, this point can be anywhere around a imaginary circle around this. This distance can be everywhere. Everywhere, this is the distance that is r. Correct. So this is the what we can draw as a equipotential surface. It will be a sphere. It is a surface. Okay. So this is a equipotential surface. So all the points combine and gives us one particular surface where the potential energy is same. Okay. This can be another equipotential surface where the potential energy is same, which is at exactly a certain distance away from the center. Okay, let this be some r dash. So another, so like that we can draw multiple equipotential surfaces. Now one unique thing that we need to remember about equipotential surfaces is that the equipotential surfaces are perpendicular to the field lines. Okay, so if the field lines is going like this, then it will be perpendicular to the field line. So this is something that we need to always remember. Okay, so gravitational field strength is usually calculated, and we can draw the direction of the gravitational field using field lines, but we can also calculate gravitational potential, and we can calculate and draw equipotential surfaces. Okay, I have a couple of examples that I can draw. For example, if I have three planets, okay, let this be planet M and this planet small m. Now the field of these planets looks like this. It will be inward attractive field. Okay, now smaller object will have less number of field lines because its field is less strong. But between those planets, there will be a point where fields cancel out. At that point, the lines diverges. So we can draw gravitation field lines like this, and it will be towards. It is an attractive force. So it will be towards. Now, all we need to do is, if I want to draw gravitation equipotential surfaces, all I need to do is draw like a perpendicular lines to this, and then connect all the lines. We get one equipotential surface, like something like this. Then we can draw more perpendicular lines, okay, which is exactly at same distance away from the center. Make sure that it is perpendicular. Okay, and then we can connect this. Now the equipotential line won't pass through this because potential is constant. we can connect something like this. So these are the collection of all the points which are perpendicular to this. Okay. Now, based on this, we can also have certain question. For example, if I have equipotential lines like this at different potential, like say -3V, -2V, -1V, and let's say I have a distance between them as 2 meters each. Okay, I can calculate the field line or what is the strength of the field or direction of the field. Now, the equipotential surfaces are stronger towards the source. So, and the force, the gravitational field strength must be attractive. So, it must be from pointing from the right to left to the always to the higher potential. So, this is the gravitation potential, and it has to be perpendicular. Now, can we calculate the strength? Yes. All we need is the difference in V over difference in R. Difference in V, I can take any two, it is like difference is 1. Okay. So, that will be the case. Okay, like -3 minus of -2, like this. And the distance between those two lines is 2. So it will be -1/2. Okay. So this is how we can calculate exactly where the lines are located and whether it is equipotential or not. We can confirm that if the gradient of those lines is 0, or if we calculate the difference, if that is 0, in that case also the gravitational field strength will be 0. Okay. Now, one thing that we will do is now we will learn about energy. Okay. So energy we will talk about is the one important energy is the kinetic energy of the orbiting satellite. Okay. So for example, when we see an object that is orbiting a planet of radius r, a distance small r, at this distance, if this object has some velocity v, that is orbital velocity, it is given as gm over r, and we can calculate the kinetic energy very easily, that is half mv square. So it will be, if I substitute this, it will be gm over r, so we can get half gmm over r. Okay. Now, what if I want to find the total energy for this case? The total energy turns out to be kinetic energy plus potential energy. Kinetic energy we already have calculated, that is half gmm over r, but the potential energy is negative gmm over r. So we will get this as -1/2 gmm over r. So what we get from this is the total energy is less than 0. And this is something that we always find when the object is trapped inside the field, okay, which cannot escape the field line, will always have total energy to be less than 0. Okay. So for circular orbits or elliptical orbit also, the total energy has to be less than 0. Okay. And the final thing that we will talk about in this is that the energy will be conserved in every case. So if the object figure out that it needs to slow down, it needs to reduce the velocity, in that case the object needs to move further away. Okay. So lower the velocity, further away the object needs to have to move, and higher velocity will make the object move closer to the planet. Okay, so that is the case. Now, when does the object will escape the gravitational field? This is the concept of escape velocity. Is that when the kinetic energy at the time of launch at the surface of the planet is greater than potential energy at that point or at that surface, then the object is able to escape the gravitational field of the planet. So in this scenario, we can see that if the kinetic energy is greater than potential energy, kinetic energy is usually given as half mv square, while potential energy is we have gm m over r. Now I'm talking about magnitude wise, and we can ignore the negative sign here. Okay. At this point, what I'm talking about is that the total energy. Okay, what we are supposed to find is the minimum. The total energy has to be greater than or equal to 0. Okay, so taking this condition, so kinetic energy plus potential energy must be 0 for the minimum velocity if I want to find minimum velocity to escape. So that will give me half mv square minus gmm over r is equal to 0. And if we find some moving some term, we will get escape velocity to be 2gm over r. Now here r has to be the radius of the planet because we are talking about the surface. So radius of the planet. So it only depends on radius of the planet. It only depends on the mass of the planet. It does not depend on the mass of the object. So whether you are launching a small ball or whether you are launching a big elephant, it will require the same escape velocity. Okay. So this is the case that we like to explore here. Okay. Now, one important thing that I will like to make a note for each case is that at any point, the gravitational field or the gravitation energy, okay, the gravitation field being conservative, make sure that total energy is always conserved. So basically, we can take any 2 points and equate the kinetic energy and the potential energy at that point to kinetic energy and potential energy at any other point. Okay, and this is where it is important. Now, let's say I have 2 points inside a field. Let's say there is a planet. Okay, and I have 2 positions. There is RA, that is for a point A, and there is a point RB, which is at another level. Okay, this is point B. So here what we will talk about is how do I move from point A to point B, and what is the work done in moving to point B? What will be the gain in velocity or loss in velocity? Okay, if we are moving. So we need to understand work done in moving a mass is a mass times change in gravitational potential between 2 points. Okay, so here we can write this as W is equal to M delta Vg, and here I can calculate potential at A is minus Gm over Ra, and Vb is minus Gm over Rb. So the work done would be M times minus Gm, the final point, that is Rb, minus Gm over Ra. Okay, and we can rearrange the terms to get this. And let's say if I have a kinetic energy at that particular point, let's say at V, okay, so we can also calculate how much the kinetic energy have changed between the points. So this is just like conservation of energy, but we can find out the work done. Now this work will change the velocity of an object, and which we can calculate here. Okay, so this is what is conservation of energy looks like in terms of gravitational field. So in HL part, this much only content is there. We have covered everything. Okay.